Okay, testing. Okay. Assalamualaikum and good day to all of you. So this is the second video for the chapter 3 mechanical properties. Okay, let me share you my slide. All right. So we stop from the video 1, we stop until here 3.2. Okay, and now we will begin with 3.3 Hooke's law. Okay, so this law is actually not new for you because I think you learned it before during the physics subject during the secondary school, or maybe during the A-level study, foundation study, you learn about the physics, okay? And this is just a recap that just want to relate between the Hooke's law and also the thing that we learn in solid mechanics. Okay, what is Hooke's law? It is discovered by Robert Hooke in 1676 using springs, and it can be known as a Hooke's law. So what he did is actually he did a lot of experiment, okay, using spring, and he studied the relationship between the load, okay, the deformation, okay, the stress, and also the strain. Okay, and the second statement there, Hooke's law define the linear relationship between stress and strain within the elastic region. So, okay, Hooke's law is only applicable for the linear relationship, okay, which is happen to the elastic region only, okay. Once the material entering the plastic region, so there is no more Hooke's law available, okay. And number 3 is that most of the elastic region correspond to linear elastic response. Okay, linear elasticity refers to the notion that stress is linearly proportional to strain. Okay, so you just keep in your mind that the stress is normally linearly proportional to the strain. Okay, so as simple as that. You learned the stress strain diagram before. You can see the elastic region having a linear curve. That's it. That one is a Hooke's law. Okay, it's as simple as that. In elastic region, the slope of the stress strain curve is a Young's modulus. Okay, the one that you find, the one that you find the gradient from the slope is called as a Young's modulus. Okay, that one is a Young's modulus. Okay, so you have this slope. So this slope stress sigma. So this gradient is E. Is E. We call it Young's modulus or modulus of elasticity. Okay, whereas the sigma is equal to stress and epsilon equal to strain. Okay, so this is what we apply Hooke's law in stress strain diagram. Okay, so E can be used only if a material has linear elastic behavior. Okay, keep in mind that not all material behave linear elastic. For our skin is not behave like elastic. Okay, our skin behave like it's a flexible. Okay, it is non-linear. It is elastic but non-linear. But for the Hooke's law, make sure that you understand this Hooke's law is only applicable for linear elastic. So for example, our tendon, our skin, our uh, ligament, okay, they behave non-linear. So for example, they will be behave like this one. Okay, the curve will be not linear. Okay, so this is non-linear. Okay, still elastic, non-linear elastic lah. Okay, because it is elastic, it can return to its original position. That one is elastic. Okay, so we move to the next one. Okay, strain hardening, the one that you discover previously. Okay, from here, yeah, here. Okay, strain hardening. So we will look in detail what is a strain hardening. So strain hardening, when ductile material is loaded into a plastic region and then unloaded, elastic strain is recovered. So means that you have a rubber band. I take a rubber band. You pull the rubber band until at the certain point, the rubber band entering the plastic region, which is strain hardening region lah. Okay. When you pull it using your finger, you apply external load, and then you release the load. Okay. And the rubber band will not return to its original position. So it will entering the strain hardening region, and we found that elastic strain is there. Okay, this is a simple explanation. Number two, the plastic strain remains, and the material is subjected to a permanent set. So once it is entering the strain hardening, you release the load, this rubber band will not be returned to original position, will be permanently deformed. Okay, permanently set. Okay, and number three, from the figure you can see there are two figures there: specimen loaded beyond yield point A to A prime. So the initial part, when you pull out the rubber band, okay, the first curve will be happen. Okay, until certain limit here, we call it this one is already entering the plastic region. Plastic region. Okay, so once plastic region, you cannot return the material into the original position. Okay, so you pull it until here, for example. Okay, and you release the rubber band. Okay, you release the rubber band. Okay, so we will introduce another slope. This one. Okay, this one. Okay, I make a flow like this one. Okay, you pull the rubber band until entering the plastic region, then you release it. So once you release, there is another slope. We introduce another slope. This is what we call it unload slope. Okay, loading slope and unload slope. Okay, so when this happen, there are two different Young's modulus. Okay, the first one is the first curve lah. It is the first slope. The second one is the second curve, the second Young's modulus. Okay. All right. So in between O to O prime, we call it permanent set. Okay. In between O prime to the line of A prime here, we call it elastic recovery. Okay. It is a strain recovery lah. Okay. And when you plot another graph, okay, you can see mechanical hysteresis. Okay, so we have some other energy that's stored in the material, like, to make sure that the metal is behave elastic but permanently set. Okay, so what is strain energy? When material is deformed by external loading, it will store energy internally throughout its volume. Okay, it's deformed by external loading. I pull it again, the rubber band here. Okay, so the rubber band, okay, will store energy internally. Okay, why store? Because it has to has energy to sustain the dimension of that material, of that object. Okay, so energy is related to the strain called strain energy lah. So we have a strain energy. Okay, so if you want to break something, you have to fight with the strain energy. If you want to become the winner, means that your energy is more higher than strain energy. Like that. Okay, this is the analogy lah. Analogy. Okay, you want to break someone. Okay, let's say you are fighting you're fighting someone. Okay, you want to become a winner, for example. So you have to make sure that your energy is higher than their strain energy. So this is an analogy lah, analogy. Okay. Not only we do have modulus of elasticity. So another modulus, we call it modulus of resilience. Okay. So when stress reaches the proportional limit, okay, proportional at a certain limit here, okay, here I put it here, okay. So the strain energy density is the modulus of resilience, or we call it UR lah. Okay. So the modulus of resilience is actually the area under the curve, under the graph, okay, under the curve, okay. So you become the equation is very simple because it's an area under the curve, okay. The equation is UR equal to half, okay, sigma times with epsilon, okay. Area under the curve, very straightforward, okay. This one is sigma, this one is, sorry, this is epsilon, this one is sigma, okay. Or can be written as this one, okay. Half sigma power of 2 over E, okay. So we just substitute this, okay, because in the previous slide, we show you this one. Oh, I forgot to put this equation in this video. So it should be sigma equal to E epsilon, okay. Okay, so you just put this equation, okay, into it. You will get you put equation epsilon equal to sigma over E, okay. So you will get this equation, okay, as simple as that. So basically you just remember the first one lah. Modulus of resilience is area under the graph, okay. Very simple, very simple. So if the question asking you to find the modulus of resilience, just find the area, that's it. Just find the area, okay, that's it. Or maybe the question will be giving you sigma and also epsilon values, okay. Values at the proportional limit, okay, which is Pn and which is Pn, okay. So you have to understand that every sigma having different value lah. This one is sigma Pn, this one may be sigma yield, okay. So having different values lah, okay. Apart from that, we do have a modulus of toughness, okay. We call it UT, okay. UT represent the entire area under the stress and strain diagram. So the strain energy define the total energy of the particular material to sustain the load, okay. It indicate the strain energy density of the material just before it fracture. So this is the area under the graph, okay. Right. So we move to the last subtopic, which is Poisson ratio. This is also a mechanical properties. Okay, you learn about many things in this topic. Okay, Young's modulus, yield strength, ultimate strength, fracture load. Okay, modulus of resilience, modulus of toughness, Poisson ratio. Those all are mechanical properties. Okay. So this is the parameter in mechanical properties. But normally the important one is only two, Young's modulus and also Poisson ratio. Okay, but you have to know the other part, the other parameter. Okay, the important thing are two elements, Poisson ratio and Young's modulus. Okay, the other one is not really important, but you have to know. Okay, Poisson ratio, mu. Okay, we call it mu, or it's something like V lah, mu, okay. State that in the elastic range, the ratio of these strains is a constant, okay, since the deformation are proportional. Okay, you have to understand the ratio is constant, okay, because the deformation is proportional. The lateral and the longitudinal axis, okay, having constant deformation. Constant strain, okay, strain deformation. Okay, so we do have this equation, mu equal to negative, okay. It could be epsilon lateral side over epsilon longitudinal side, okay. So again, Poisson ratio is dimensionless because it is referred to epsilon. Epsilon is also dimensionless. Okay, so Poisson ratio is also dimensionless. Okay, so typical value should be 1/3 or 1/4 lah. Okay, so normally we will just find below than 0.5. Okay, normal value is below than 0.5. Okay, alright. It should be sorry, the sign is wrong. It should be below 0.5. Okay. Okay, mu has a numerical value that is unique for a particle matter, homogeneous and isotropic. So this terminology, I think you already know in biomaterials. You learned in biomaterial last semester. So if I want to repeat again, maybe in the physical class lah. Okay, homogeneous means that every single point having similar properties. Isotropic, every single axis we have in 3D, we have 3 axes. Okay, every single axis having similar properties. So this is the homogeneous and isotropic. Okay, I just give example. You have a femur bone here. Okay, so this is the point that you want to study about E lah, for example E. So E1, so E2, this one E2. Okay, if homogeneous, E1 equal to E2. Okay, so this is homogeneous. Okay, homogeneous. But this one is bone. Bone is non-homogeneous. Okay, this one is only showing you example. The bone is non-homogeneous, but I'm just showing you the example. E1 in E2 should be similar if the material is homogeneous. So how about isotropic? So isotropic, you taking E2 for example, and E2 in 3D model, we have 3 axes, X, Y, Z. Okay, so every single axis having different properties as well. Okay, so let me put EX, EY, and EZ. Okay, so if isotropy means that E at X equal to E at Y and equal to E at Z. So this is isotropic. Okay, so as simple as that. Okay, so for the Poisson ratio equation, negative sign indicated longitudinal elongation, positive strain, causes a lateral contraction, negative strain, and vice versa. So you just imagine that if you pull a rubber band here, the other side will be in the one side will be compressed, another side will be tension. Okay, the compression will be in negative value. So if you have negative epsilon over epsilon, you become negative as well. Or you will have epsilon positive, this one positive, over negative epsilon, become negative as well. So as simple as that. Okay, we become always negative. Okay, so lateral over longitudinal, okay, lateral long, okay, so we will be always negative. Just keep in your mind. And what is lateral, what is the longitudinal? Okay, so this is the longitudinal. Okay, and this is lateral side. Okay, so for the left part, the case where the longitudinal is tension, so it become positive. This one become negative. Okay, compress. And how about the other one? This one is vice versa. So this one is long. We become compressed. Okay, become negative. And the lateral one, lateral, become positive. Okay, become positive because it's elongated. Okay. Okay, we move to the example and then we finish it. Okay, we move to example. Only one example for this topic. All right, a bar made of E36 steel has the dimension shown if an axial force is applied to the bar. Determine the change in its length. Okay, the change its length. So just get the idea or information. What is the thing that you have to find? The change in its length is actually what? is actually what? You have to think before you answer. It should be the delta lah, the changes. Sorry, not it, delta. Okay, and you have to find the change in dimension of cross section. So you have to find the changes as well in dimension. In this dimension, we have y and x. So it should be changes in x, changes in y. So it become delta x, delta y. So those three, you have to find it from the figure, from the statement as well. Okay. The matter behave elastically. Okay. So normally the question will be mentioning about this lah. Okay. If not mentioning that, normally we can consider default, where all materials in the question will be behave elastic. Okay. So Young's modulus is given, Poisson ratio is given. Okay. And then you can start to find the changes. Okay. So just the way that you want to answer the question is you have to think about the thing that you want to find, which is three unknown here. And then the second thing is that you can jot down or you write any equation that you remember. For example, sigma E over E epsilon, for example, L minus L naught, okay, equal to changes over L naught. When you write the equation, you will see, this is the thing that you need to find. So normally, this is the way that I normally answer the question during my study, undergraduate study. Okay, so I write everything, the equation, on the paper. So I will see what is the thing that I can use the equation. Okay, so L naught is given. Okay, epsilon, you can get the epsilon from the Poisson ratio. So Poisson ratio is given there, mu equal to negative epsilon lateral over long. Okay, lateral over long. Okay, so in this case, which what do you call it, epsilon you want to use, either lateral or longitudinal. So we have to get information there. We have to get information there. But of course, in this case scenario, okay, in this case scenario, the length is this one. This is the length. Okay, so this is the length. Okay, so you have to use the longitudinal. Longitudinal. This one is long. Long. This one is lateral. Okay, so you have to use longitudinal epsilon to get the changes. Okay, clear? So the thing is that you jot down everything. So another equation is E lah. Okay, sigma over epsilon. So you jot down every single equation. Okay, and then you can start with the calculation. This is the normal procedure or steps that normally I did it during my undergrad studies. Okay. All right, so we move to the next one. Okay, you have this same figure. You have to find the what do you call it, sigma set first. Okay, because the changes in its length is belong to longitudinal axis. Okay, so we have a sigma z lah. Sigma z equal to P over A. So we have P there, we have A there. Okay, and then you will get the answer lah. Okay, then we'll get the answer. Okay, so this one should be in bracket. Okay, you will get the answer. And then the next one from the table, not table lah, because the question already giving you the what they call it, elastic modulus. Okay, just use the equation there. You will get epsilon, okay, equal to sigma over E. So E is given. Okay, sigma you already calculated from the beginning. Okay, you just insert the value into the equation and then you will get the final answer. Okay, as simple as that. Should be negative. Okay, so again, I repeat again, if you are not write any equation, you will not getting the idea on how to solve the problem. So better to write everything and then you relate which equation that you want to use, okay, which parameter that you looking at, okay, and then you can straightforward use the equation. Okay, so this one is a longitudinal. Okay, okay, and then this one is not yet finished lah, because our aim is to find, oh, sorry, our aim is to find the, what do you call it, delta, delta for long lah. So from data, you have to use the second equation of sigma here. Sorry, not sigma, epsilon. Epsilon equal to L minus L naught over L naught, or the delta over L naught. So just straightforward. Okay, just straightforward. You will have this formula. Okay, epsilon equal to this one. Okay, delta over L, and then the value of epsilon is calculated. The length is 1.5, and straightforward you will get the delta. Okay, so the answer is here. Okay, so delta z equal to epsilon z. Okay, just substitute the value. Okay, and you will get the answer lah. Okay, so this is the answer. So you will get you get the first answer. Okay, so back to the question, you already get the changes in z. Okay, changes in z, which is the delta z. So the next step is to find the delta x and delta y. So delta x and delta y, you have to relate with the Poisson ratio equation or Poisson ratio value. Okay, so the Poisson ratio value is given there. You know the Poisson ratio equation, then you can use it to find the deltas x and y. Okay, so the contraction strength in both x and axis are, so we have the delta x, okay, equal to epsilon, no, should be x, ly, ls, okay. Sorry, I think I made a mistake. Sorry. So let me delete it. Sorry. Alamak. Huh? Let me delete it. So to advance. Okay. So you can, because we have this equation, v, sorry, let me change the color. V equal to negative epsilon lateral, epsilon long. So long is equal to z lah. Lateral should be x lah. Okay. Okay. So in this case, epsilon x and epsilon y is similar. Okay. So you just use this equation, okay, where the epsilon x equal to epsilon y, okay, equal to negative v epsilon z. Okay. So this equation is coming from the original equation. So you just substitute the value negative 0.32 in bracket. Okay. And then you have this one and this one. Okay, I will get the final answer like that. Should be micromillimeter. Okay, so once you have these two, then you can find the elongation. So just remember, elongation or the delta x equal to sigma, sorry, not sigma, epsilon x ls. Okay, delta y equal to epsilon y ly. Okay, so you will use this formula. Okay, you will get the answer straightforward. Okay. Okay, just substitute the value. Okay, the value is similar for the epsilon x and y, so just substitute it. Okay, negative, okay, in bracket, so you will get the answer. Okay, micro. So this is the answer. Okay, so before you end the calculation, you have to think again. Is it the answer is correct or not? So how you check the answer is like this way. So this one is the answer for Z, longitudinal. This one is the answer for the lateral. Okay. Again, you refer again the figure here. Okay. It is a, a tensile load. Means that the longitudinal will be more longer. So more longer indicating positive value lah. So this one positive value. So the answer is correct. I think I mean in terms of the direction lah. Okay, the direction positive is correct. But for the lateral one, when you have a rubber band, you pull it. Oh, sorry, already broken. Already entering the plastic region. So no more elastic. Okay, so when you pull out the rubber band, okay, rubber band. Okay, so the lateral side will be squeezed, will be small. Okay, will be small. Okay, so it become squeeze, will become negative. So that's why the direction is negative. So this is the way that you want to confirm the answer lah. But this one is only to confirm the direction lah. Okay, the direction. Okay, about the magnitude you have to reconfirm in the calculation. Okay, I think that's all for the topic 3, mechanical properties. I hope you understand everything. If you have any question, just let me know. You can come to my lab, but before coming, please contact me because I'm not always available. Okay, I have many things to do. Okay, make sure that you contact me first before you come to my lab, before you come to meet me. Okay, to make sure that I'm free. Okay, so we have a test on Thursday. Make sure that you study chapter 1 to 3. I will be uploading the sample test soon, okay, in the e-learning. So you will have some idea what kind of question that normally we ask students to answer, okay? And then you have to do a lot of exercise. Don't only look at lecture note, okay? Don't just look and just look. You have to practice many times, okay? Because the solution is different based on the question, okay? Many questions have different solution, okay? So I think that's all for me. Thank you so very much. See you next week in the physical class. Bye.